I'm audible, right? Fine. So, welcome to Horizon, the Physics and Astronomy Club of IIT Madras. We conduct many series of lectures, in which Q2Q is one of them, where we invite different professors from different backgrounds. Today our guest is Professor Jim Libby, an experimental physicist from the Department of Physics, IIT Madras, and he is going to present an engaging talk, Inward Bound, an Introduction to Nuclear Physics. I now call the professor. Please, sir.
Okay. So yeah, I will hopefully not need to use a microphone, but if it's a problem, just let me know and I will change over. So this has nothing to do with my talk. I'm using PowerPoint and very helpfully Copilot is there to tell you how to make your slides engaging and nice. Unfortunately, this one I realized as I was going through this, I'll just let it run through once more. Where is it? Where is it? There we go. So essentially, this is the problem with AI in a nutshell, right? That it doesn't know what cosec is, or hyperbolic cosine, a cosec, and you know, there's no doubt, you know, 20% other rubbish in this. So I didn't resort to any other AI tools. You have organic intelligence to blame for the rest of the talk, all right? But yeah, I was a bit surprised. This is what they came up with, just that title. They came up with a load of mathematics flying towards you. So anyway, enough of this. So before I start, I'm not going to fully generate the talk myself. I'm going to ask you what you know of nuclear physics, or what you would like to know. And then I'm going to find there's a horrible mismatch between what I've done and what you know. So just just call out anything you can think about nuclear physics which you interesting, different to other areas, or you know nothing. Okay. Not a tree. Okay. I will not be talking about defense applications of nuclear power. If you are interested in this, there is an excellent popular science book by Richard Rhodes called The Making of the Atomic Bomb. And not only is that a book about the Manhattan Project, also the German version of the Manhattan Project, the Russians spying on the Americans to get all the information about the Manhattan Project, it's also a history of quantum mechanics, essentially. It's an excellent book. So I decided not to do this because that's really another talk. So look this guy up. He's written 2 books about nuclear bombs. He's not a scientist, he's a historian. But he's got very, very good scientific understanding and the books are excellent. Anything other than the bomb? You know it's there at the middle of every atom. That's it, is it? Okay. So it's good Raghu left. He's taught some of you, right, in this this semester, or maybe not. So I can't do justice to all of this, but I'm going to talk about essentially 3 blocks of things. One is it's very, very different to pretty much every other area of physics that you come across. And that's because the forces at work in nuclear physics are not those that you're familiar with. Okay? So every human experience is an electromagnetic interaction. Okay? That's what we respond to, we see. In even matter moving, it's the electromagnetic impulses that you feel the air moving, but it's an electromagnetic effect. That's the pressure on your skin or whatever. So, or in your ear. So everything is electromagnetic that you really experience. But we also have a good sense about gravity because things fall down, right? So you think you understand gravity, but gravity is quite complicated in a different way. But what goes on inside the nucleus, you have no feel for. You can't visualize it, you can't really understand what's going on until you do experiments, which I don't have a lot of time to talk about, but I think it's very important to understand why the forces at work in the nucleus are so different to electromagnetism. Okay? And really how we learn a lot about that is through nuclear decay, and I'll talk a little bit about nuclear decay, and that leads me to particle physics in a way. Then I want to talk about two aspects of nuclear physics which are very important that you see everywhere. One is the sun, and the other is 21 centimeter transitions in hydrogen. Essentially that's an area of great interest for anyone doing radio astronomy. And I just want to explain why that's a nuclear phenomenon. I won't talk a lot about the cosmology. You probably have other speakers to talk about that, but it's just to show that these nuclear effects are there, and they're important for us to be able to leverage other areas of physics. Now, I'm cheating here a little bit. I'm not a nuclear physicist. I am a particle physicist, okay? And my interest in nuclear physics is because it was the gateway to understanding particle physics. And in the last part of the talk, I'll try and explain a little bit about what I mean, referring to some of the things I've introduced in the first part of the talk. Sadly, this talk's a little chaotic. I haven't had as much time as I would like to prepare this, so please bear with me. There's going to be some bits I'm going to do on the board, some bits are in the slides, some slides are very sparse, but I'll just try and talk around them. It's not how I would normally teach, but you're not here for a lecture, right? You're here for some, well, entertainment maybe, but not too much. And questions, yes, good, questions already. Are you questioning why you're here, are you, or?
Why does this force exist?
Why does it exist? That's a pretty big question, no? So maybe I'll dodge it for now, if that's okay. One thing about particle physics which people should realize early on is it's not a why subject. We have lots of unanswered questions. I'll come to this. It's a how subject. It's how things work. And the two additional forces that we require to describe the nucleus are very much a how the nucleus works, okay? Now, the why, and there are maybe additional whys we don't know about, and I think that's most likely, okay? Any other questions? But questions are welcome anytime. I think I'll probably speak for about an hour, so I hope there'll be time for questions afterwards. Those of you I've taught know that I don't mind being interrupted, okay? So it's quite fine to ask whenever you want. And others know that when I make a mistake, please tell me, okay? Right, so the nucleus. This can be helpful in some ways. There are, of course, many problems with this visualization of the nucleus. One thing is it certainly isn't colored in this way that we'd imagine, given its size. But the most important thing I want to say in the first part of this is a little too large, all right? The nucleus inside the atom is very, very small. It's about 5 orders of magnitude smaller than the atomic size, okay? So it's a very, very localized region even inside the atom. Most of the atom are the wave functions of the electrons and how they interact with one another. The nucleus is there as this small fixed point of positive charge. You can do pretty much everything in atomic condensed matter physics with this kind of model. Not quite everything with atomic physics. Some of the innermost shells in the electron are perturbed because the nucleus has a finite extent, but it's not possible to, you know, you can get away with describing it really as a delta function with a certain charge. And of course, you know, the electrons are garbage here, right? We all know that. A more useful picture is this. This actually gives a reasonable sense of the scale of the nucleus. So if you're at whatever your favorite cricket stadium is, I probably should pick Eden Gardens here, I think it's the largest. And you had a cricket ball right in the center, and you were right back at the farthest tier, you're getting roughly to the sense of scale for what a nucleus is, and where the electron orbitals will go out to. Even the innermost shells, it will go out even further than that. So you're talking a few centimeters to kilometers, okay? And I won't continue to talk about cricket, because in the end, England, India, and things will come up, and I don't want to talk about that. But an important first question about nuclear physics is why it's so small, right? Why is the nucleus this tiny region? It's not an answer I can give you fully. I'll get to it at the end, where I'll give you our best explanation. But for the moment, let's just think about the size. Okay? So the mere fact that it's so small is telling us that there's another force in play. Further, right, half the stuff in a nucleus is traditionally charged. And we all know like charges repel one another. So this force is very strong and overcomes that. That's probably what you learn at school, right? This is how the nucleus works. But it's even more peculiar once you start doing some very basic studies of the nucleus. And one way you can study the nucleus is just measure its size. It's actually not trivial how you do this, but it's essentially a version of Rutherford scattering. If you've got high enough energies, you can work out how your pattern of deflected particles, whether they be neutrons, electrons, alpha particles, how they distribute, you can work out the size, how the interference pattern changes. And what you see is essentially that the nuclear density is constant as you increase the size of the nucleus. So this is what this plot shows here. So here we're going all the way out to lead, down to carbon. On the vertical axis, you just have the mean square average of the radius. It's what you end up measuring when you do the scattering experiment. Essentially, this is the radius in Fermi. And this is the atomic mass number, A. It's not, the resolution is not particularly good, which just tells you how many nucleons there are in it. And it scales pretty well as just A to the cube root. And that R0, the constant of proportionality, is around a Fermi. Now, why this is peculiar is if you look at something that's held together, say, by gravitational forces or electromagnetic forces, there is huge pressure on the innermost part coming from the fact that the force is extending out and pulling things further in. So if you look even at the Earth, the core is much denser than the mantle, and this is just because everything is under pressure. Okay? And that pressure is because the forces are long range. Gravity is a long range force. It's infinite range. Electromagnetism is an infinite range force. This is easy to explain if you just say the force between nucleons is basically just seen by its nearest neighbor. So once you're outside a nucleon, the force has gone. And there's a good reason for that, but it's actually really related to particle physics, that these objects have no charge in terms of the strong interaction. Okay? And this means that they're just packed together, feeling its nearest neighbors. And you can actually describe a lot about the nucleus with that model, and I'll come to that in a couple of slides. So one comment here, I'm going to have a lot of figures taken from this one book, and I don't attribute all of them. This is Crane's Introduction to Nuclear Physics. It's quite an old book. I think it was written in the early 80s. Maybe the most recent edition was then. But it's encyclopedic. It has everything in it. So if you're really interested in the details of nuclear physics, this is as good a place as any to look. And it's a reasonably good description. A few things are out of date. Don't read the particle physics bit. But otherwise, it's a very good book. And I've taken a lot of figures from there. Right, so the size we know is a few Fermi. Now we have to think about the energy scales that entails. So what we have are particles trapped in a very small region. So that's your simplest quantum mechanical problem. That's particles in a box, okay? And in your quantum mechanics courses, if we haven't done quantum mechanics yet, you will do soon, you will work out that a quantum mechanical particle trapped in a box has energies described by this formula, where this is the mass of the particle, this is the size of the box, and these are principal quantum numbers, which are integers, which go up. So this is a order unit 1 constant here. Okay? So I can just plug numbers into this based on a 3 Fermi-sized object, which is a mid-sized nucleus I had on the previous slide. And we work in the natural units for nuclear physics, which are mega electron volts and Fermi. So you can describe the combination of reduced Planck's constant and the speed of light as 197 MeV Fermi, which is the most useful number in nuclear and particle physics. You put in the other factors, mass of the proton, 938 megaelectron volts, and you get out 20 MeV. And basically all nuclear phenomena are of the order MeV, ranging from 1 MeV to a few hundred MeV. This is how nuclear interactions energy scale. So it just comes from the size and basic quantum mechanics that the things being trapped in that kind of region of that mass will have to have energy of about this kind of number. So this is easy to understand, and that's why I just wanted to start with this relatively straightforward idea. But how those particles are bound together in the nucleus will tell us a little bit about how we're getting towards these new forces that we're talking about, the strong nuclear force. So that the quantity here is the binding energy, which is just the sum of the masses of the protons and the neutrons that you have inside a nucleus. So this is the Z and this is the N. So I should, so you'll have, let me just remind everyone of what I'm talking about here. You've done more chemistry than me. So if I have, for example, carbon here, 12 is the A, 6 is the Z, and the N is the A minus Z, okay? But you will have done this a great deal, but this is the standard nomenclature as followed. So as a function of this mass number, what's plotted here is not the total binding energy, which is what's written here. It's the binding energy per nucleon, so it's divided through by A, okay? And this axis, if you can read it, is in MeV. It's going between 0 and 10. Down here, you can't see very well, this is the deuteron. That's nuclear hydrogen. 1 proton, 1 neutron. It's the simplest bound state. Not very well bound. It's like 1.2 or something, I think. Maybe a bit less. Yeah, no, 1.2 is the number I remember, MeV. Maybe different. And then it goes up until the most tightly bound nucleus is iron, and then it starts to fall off again, okay? And there are a few ripples in this, and there are some odd things that happen, like helium's up here and it drops down to lithium when it's very light. We'll come back to that. But this formula basically describes everything you need to know about a given nucleus, and it's well described by something that has a terrible name, which is the so-called semi-empirical mass formula. All right? It is not truly empirical, hence semi-empirical, but nor is it a fundamental thing, so hence it gets this title, right? It is a parameterization based on physics. And it's quite important to try and understand how this works, okay? So here, I plotted this axis, or Crane plotted on this axis, the binding energy per nucleon. And the first term is just the binding energy that comes from a nucleus feeling the force of the nucleons surrounding it. That's that nearest neighbor force, okay? So I show this again because if you imagine one of the central ones, it's got a number of nearest neighbors packed closely around it. It will have some strong potential associated with it. We're talking particle in a box here. So what we're really talking about for any radial distance and the potential, it'll be minus. So if I have 0 here, essentially I have some well like so, and this is where our nucleon is at the bottom of this. And that's pretty much fixed for every nucleon, okay? Doesn't care if it's a neutron or a proton. We'll come back again to this charge independence. So this is the first term. This is the volume term, they call it. So every nucleon feels this. This has to be corrected because these ones on the outside do not feel that much potential, okay? So they'll be in a less deep well if you're on the surface, okay? So they're less well bound. So you reduce the binding energy depending on the surface area of the nucleus, and this is the so-called surface term. So it's proportional to the radius squared because it's a surface. I'm dividing through by the total number of nucleons, so it goes as 1 over the cube root of A. That's what this shape comes from. We can't completely ignore the fact that we're trying to cram together a load of positive charge in a small space. So there is a further correction, the so-called Coulomb one, which of course gets larger with the number of protons. It goes essentially as z squared. But of course, a proton can't feel its own force, so that's where the -1 comes from. And then there's a scaling that depends on the separation, the 1 over r type piece, which again goes as A is the 1/3. I'm dividing through by A, so this is overall A 4/3. So this is this line. So this is, you subtract a bit for the surface, you subtract a bit for the Coulomb. Coulomb doesn't matter much here, matters more the further out you get. So in all of this, I've ignored quantum mechanics, right? That's where the last term comes from, this so-called symmetry term. So whoops. So these are energy levels you have in any quantum system, right? You have a series of levels, and in an atom, the most simple way you would do this is you fill these with 2 electrons, and then the next one, etc. Okay? Now, there can be further degeneracies based on the angular momentum. I'll show that on the next slide. But for this asymmetry term, you're ignoring even that, okay? There's nothing said about the angular momentum. But what this means, okay, protons and neutrons are fermions, just like the electron, right? They obey Fermi-Dirac statistics, and they obey the Pauli exclusion principle. So they also have a filling principle, right? So we must assume that there's going to be some quantized energy levels in our nucleus. I'll show those in a minute. And you will have a neutron and a proton, well, actually 2 of each, filling each of these states. So if you get an asymmetry, if I suddenly start filling protons here, these ones are going to be less well bound than the neutrons on this side, okay? So this asymmetry term is saying if I've got more of one type, some have to be less well bound because they're in these quantized steps, okay? And that explains this term. So I have 2z minus a, which is essentially the number of protons less the number of neutrons. And then it's symmetric, so it's squared. And then there's this A term, which is essentially describing this effect that the energy levels get more tightly closer together the more you have to fill them. That's parameterized, it's not exact. I'll show you the exact when I do the shell model. But with this, essentially we get back what I had on the previous slide, almost. Yep.
What does this graph represent again? The previous one?
This one. It's the same thing. It's the binding energy per nucleon.
So these are the correction terms.
Yeah, so I start with 1, then I add the surface term. I'm not adding, I'm subtracting, because these are making things less well bound. Each of these make things less well bound, right? Electrostatic repulsion makes things less well bound. Surface term, less well bound. Pairing term, less well bound. So these are all negative corrections to this volume term, which is the strong binding from the strong force, okay? So this is all it's representing, is getting this shape right, such that with the appropriate parameters in this formula, you'll get exactly that iron is the most tightly bound nucleus, all right? This works really well for most nuclei. It's not so great down here with the light ones, and that's because of these quantum mechanical effects, which we can't model with this kind of formula. Okay? take home from this, probably should have written this, is basically this idea of a very short range force does an excellent job with these three corrections of describing how all nuclei's masses are worked out. So another thing that's different from atomic physics is masses of atoms are not particularly interesting, right? Because the binding energies that you have of the electrons around the nucleus are in the range EV, maybe the tightest bound shells, there'll be something you could get to KeV. But when you're dealing with a nucleus which is almost a GeV in weight, this binding energy is nothing. It's actually about 1 part in 10 to the 6. It's the binding energy correction in an atom. So the nucleus is again immediately different, that the binding energy plays a role. Now, a mystery for later is when we talk about the proton being made from quarks. There, the masses of the quarks are around 6 MeV, but the mass of the proton is 938 MeV. So it's completely wrong. There's no traditional binding energy here. It's to do with the strong interaction and how it works, that they're actually very massive. But that I may have time to discuss later. Okay? So, quantum mechanics of this, these shells. So when people first started studying nuclear physics, they didn't really understand what was going on, but they found certain numbers had very tightly bound nuclei. They didn't fit perfectly on our binding energy curve. They were a little more tightly bound. The classic example is helium there. And out of desperation, they were called magic numbers. Always bad to invoke magic when you're talking about physics. And it became kind of clear how they might come about. So this is back to our infinite well, but now in 3 dimensions. So when I go to 3-dimensional potentials, you'll have a radial piece, right? But you also get the spherical harmonics that describe the angular momentum of the state. So these letters down the side here are the spectroscopic notation, where you describe the first number is the principal quantum number that you have in the hydrogen atom, the N or whatever. And then the SPD describe the total angular momentum of that state. So S is equal to L equals 0, P is L equal 1, D is L equal 2. Then they got bored, and F, G, H go up normally as the letters of the alphabet. It goes on up. So what this means when you have a certain angular momentum, L, okay, you have the projection of that angular momentum on your axes of quantization. That will go through from minus L up to plus L. This is an integer. So there are 2L plus 1 different ml, and then the nucleons themselves have a spin quantum number, so there's a 2 number of ms, where there's plus a half, plus or minus a half, so there are 2 of those. So this leads to the degeneracy of the states. There's a 2 times 2L plus 1, and this is how you can do your counting of the number of states that are in here. So for P, I have L equal 1, that's 3 times 2 to get me to 6 possible states, and so on and so forth. But this is the infinite well. This has some random spacings due to the how the angular momentum behaves. Simple harmonic oscillator is nicely evenly spaced, and you get these numbers where you'd have filled shells. Neither of these potentials suitably model the nucleus. Okay, what we do have is this thing on the right side here, which is called the Saxon-Woods potential, which is essentially a semi-infinite well, okay, but with a smooth boundary. So it's parameterized by just three numbers: the depth of the well V0, this radius where we're confined to, so this would be a few Fermi, and then there's this A parameter which is just telling you how smoothly it changes. Okay, so it's this relatively simple function. You can't solve this analytically if you put it into your three-dimensional Schrodinger equation. You have to solve it numerically. Okay, and don't panic when I show you the next slide, okay? You get this, okay? So we have exactly the same as I had before for the infinite well and the harmonic oscillator on this side, where you have field levels related again to their angular momentum here. So I have the 1s, 1p, 1d, 1s, and they go on up. And they have field levels at 2, 8, 20, 40, 58. These are not the magic numbers, okay? You have to do one more thing to get the magic numbers, and that's to do a perturbation. So how many of you studied hydrogen at one point or another? No one? One person has studied hydrogen. So there's something called the spin-orbit interaction, yeah? Where you have, if you consider your electron to have a magnetic moment, and then the nucleus is revolving around it, creating a magnetic field, there's a perturbation due to that. And that depends on the direction of the spin of the electron, so it breaks the degeneracy of the states in terms of the spin. And so states start to split. And this is what's happening here, but now this is the chromomagnetic moment of the nuclear force interacting together with the particles in the nucleons that are in there. And this splits the level such that there are gaps at exactly what are the magic numbers, which are written here: 2, 8, 20, 28, 50, and so on. So this model now of the nucleus is called the shell model. And this is very good at describing, okay, the magic numbers, but it also tells you the spin of the nucleus. So in this example, on the right-hand side, this is two isotopes of oxygen. One with 7 neutrons, this one with 9 neutrons. And what happens when you have pairs of protons or neutrons is they like to anti-align with one another and have zero net angular momentum involved. So you fill up the shells. So these filled bits here contribute nothing to the total angular momentum. And you're just left with this one unpaired one here, which is in the p half state. So it's actually got overall angular momentum of a half. And that's the angular momentum of this nucleus, or the spin of this nucleus. Similarly here, this goes up to the d5 half state, which is 5 half spin, and oxygen 17 has that particular spin. Okay, so this shell model is well verified because you can measure the spins of nuclei quite easily by various ways of doing this. One is to look at hyperfine structure, which I'll talk about later, but another is to just strip off all the electrons, look at the ion that you have, put it in a magnetic field, do a Stern-Gerlach type experiment, and you'll work out exactly what the spin of the particle is. Okay, so between the semi-empirical mass formula and the shell model, you pretty much describe most of the properties of static nuclei. Okay, done ish, I think. So there's one bit I've sort of skipped over. The nuclear force is spin dependent, okay? And this is part of this pairing. Why they like to anti-align one another is more tightly bound than if they're parallel to one another. And what this means in nature is that basically there are very few nuclei with an odd number of neutrons and odd number of protons. There's an absence of nuclei with odd numbers. So the deuteron, 1 neutron, 1 proton, is there. Then we have lithium, 3, 3, and boron, 5, 5, and nitrogen, 7, 7, and that's about it. There are a few others, 2 others, tantalum and something else. But there are very few odd versions of the nucleus. And this is because if I plot here, I haven't put the axes on very well. This is the binding energy, okay? or minus the, no, it's not the binding energy, this is the mass, so this is minus the binding energy. These are the odd nuclei for a fixed A, 128, and these are the even for 128. And what happens is that there's this preferred state down here, xenon 54, with 54 protons, which is the one that's most tightly bound. And there are various paths here that lead to this bottom state, and things just decay away to this state. So this is the nuclear decays that happen. And in this particular diagram, all the decays are moving by plus or minus 1 charge. That's beta decay. But I'm going to talk about beta decay after I've talked about alpha decay. So this is now when we start moving towards the dynamics of nuclei. Nuclei are static objects. They've got mass, they've got binding energy, they've got spin. These are static properties. Now we can talk about their decays, which is where I think it starts to get more interesting. But this is the classic plot showing, as a function of number of protons and a number of neutrons, these are all the isotopes we've ever observed. Okay? Now, the black wiggly bit in the middle, those are the stable ones. These are the ones that do not radioactively decay to some other state. Okay? The stuff that's in orange have positive beta plus decay, blue beta minus, so they move things back towards this line of stability. Then up here, this stuff in yellow is alpha decay. That happens in heavy nuclei, and I'll talk about that in a moment. Then there are other ways for things to disintegrate. Very heavy atoms will fission spontaneously, and then you have this something called proton drip and neutron drip, where a nucleus will just spit out a single neutron or a single proton because that's energetically favorable. That happens in light nuclei, that's neutron drip up here, and this is proton drip along the bottom. Okay? And the white stuff they label as unknown, which means we've never seen that nucleus. Okay? But in principle, you can try and make it, but just be very unstable and decay very quickly. Okay? Now this trend that you see, this line is equal number of protons and neutrons. That's readily explained just by the semi-empirical mass formula, and the fact that you need some more neutrons in there as you cram in more protons, otherwise the Coulomb term makes it less favorable, and then balances a little bit the asymmetry term to stop it going all the way, like to make a completely neutron heavy element. Okay, so what I wanted to discuss next are these decays. I don't have very much on either of these. So alpha decay is a heavy nucleus spits out a helium nucleus. Helium is a doubly magic nucleus. 2 was filling that lowest level in the shell model, so it's very tightly bound. So the model for this is that it's energetically favorable for nucleus X to decay to X prime plus an alpha particle. So there's a net positive energy or Q value in doing that. So the model according to Gamow is that you have this helium nucleus preformed moving in the potential of the other nucleons of the in the nucleus. Okay? And then outside of this tightly bound nucleus, the only thing that's happening is the electrostatic repulsion between the helium and the remaining nucleus, the X prime. And this is this 1 over R falling off here. Okay? And this is the original quantum mechanical Talonly. Okay? This preformed helium is just bouncing back and forth, confined in this small region, but freedom is out here. And if its wave function can tunnel through, which of course it can, this is just a slightly funky shaped barrier, right? But you can actually work this out analytically using WKB approximation. You'll find there's a probability this thing will be spat out. And this model according to Gamow is very, very well represents alpha lifetimes. So tunneling is still popular today. The Nobel Prize last month was for seeing this in electrical circuits. But the original confirmation that it was such a true quantum mechanical phenomenon came from this model that described alpha decay, which is from, I think, the 1930s or early 1940s. Okay? So don't worry too much about the numbers here, but it's a very nice example of quantum mechanics in action, describing how alpha decay works. Alpha decay is a purely strong interaction. Okay? It's a strong potential and strongly bound helium, strongly bound nuclei, nothing to do with any other interaction apart from the Coulomb repulsion bit once it's outside.
Can you give me a better understanding of how we can calculate the decay time? Because my understanding is that we will be able to find the some eigenfunctions, and then assuming it is a time independent potential, we will stay in that eigenfunction. So how do we figure out because just because the wave function is present outside in that a radius, that doesn't mean that it will go from an eigenfunction to some other bit.
So
really possible.
when I introduced tunneling to you, right, we had a barrier and we have a particle approaching from one side, and then you would figure out a probability that it comes out the other side. So my eigenfunction is this essential standing wave on this side of this thing bouncing back and forth, okay? So you continually, perpetually approach the barrier from one side with this eigenfunction of this, with this value of whatever it is. It's got energy Q, essentially. So that's fine. That I can solve out inside this potential. So that's one quantum mechanical eigenfunction. Similarly, I can solve it for this point here, which it tunnels out to. Then, of course, I'd have acceleration there, so it's gaining energy, so it's a dynamic situation once it's outside. But just moving between here and here is just a classic tunneling problem.
No, so there will be a bunch of discrete eigenfunctions, and then with high energy there will be a bunch of continuous eigenfunctions.
But there's no high energy, there's one energy here.
Of this potential,
Yeah.
we'll have some discrete eigenfunctions.
Yes.
And then a continuous list of very high energy eigenfunctions also.
Yes.
Okay, now
But there's only one energy. That energy, the Q value. We're not worried about any of the other
we
states.
are sitting in the ground state.
Sorry?
Yes, most of the time we expect it to be in the ground state.
I'm telling you, it's in a state with energy Q.
Okay.
So why am I worried about the ground state? This is the model, no? Well, I don't see what your problem is.
So what is the cause of the decay?
What is the cause of a decay?
Because I expect it should stay in the ground state. Whatever the ground state is. Like if I take a hydrogen atom and I put a electron in oneness, it does not randomly appear far away.
The cause of a decay, right, is that it has a probability to happen. It's a quantum mechanical phenomenon. There's a probability related to it. It's time dependent, so you have to use time dependent perturbation theory to properly describe it. But
So you're saying that if I take the ground state and I assume that some small potential, time dependent potential is put on that, then
I'm doing nothing. This is all static.
so my question is, if I have a hydrogen atom in oneness state,
Yes?
it will not, that electron does not randomly decay.
I don't care about electrons. I've gone beyond electrons. I've gone inward. Yeah.
But then, so what is different between that system and this system that will
The
electron decay?
potential, no? Look at it. It's different. You know, hydrogen. I've just got that, right? That's my potential. It's a completely different thing, and I can solve it out exactly. And I've got my nice states and everything. Here, I've got a nucleus of a certain energy in a particular state. There's one state inside that's bouncing back and forth. It's a particle trapped in a box of a certain energy. That's it.
Like, what do you mean by bouncing back and forth? Isn't it in one eigenstate, not going anywhere? It's standing there.
It's a standing wave, but it's in motion from the uncertainty principle, because I don't know where it is. I can only confine it within that region, correct? So it has a momentum, which is meaning it's moving back and forth.
It has a standard deviation momentum.
Sorry?
It It has a standard deviation momentum.
Yeah, so it's moving. Please go and read Crane. I think everyone else will would like you to do that. You will see how this model works, okay? It doesn't violate anything beyond the basic quantum mechanics we discussed previously. It's actually simpler than that because decay itself is a time-dependent phenomenon. I didn't want to get into that because I'm not expecting.
Time dependent, where does that come from?
It's probability. Yeah? There's a probability to change states. That's it. Okay? It's the same. Are you happy with the transition in an atom? It's the same.
By some external or spontaneous.
Spontaneous bit. The spontaneous bit you focus on, yeah? It's the same idea. Okay? So if I've got something in an excited state, it will decay. Correct? Yeah. Okay. Got to move on. Beta decay.
Yes, obviously one extension.
Ooh. Can he? Quickly.
In hydrogen atom, it is the vacuum mode of the electromagnetic field that causes the spontaneous emission. Is it the vacuum mode of some other field which causes the spontaneous decay in nucleus?
Yes.
Which field is it? Or
The strong. At a particle level, it's all gluonic interactions, okay? But it's very complex because it's many body, okay? So yeah, beta decay is the other one I wanted to talk about. I'm not going to talk about gamma decay because that is spontaneous emission in an atom, just in a nucleus, things moving between levels. Not the most interesting. But this is very interesting because it changes matter. It's the only force we know which changes one type of particle to another, okay? When you're dealing with atomic physics, you preserve the number of protons, neutrons, and electrons. Nothing's created or destroyed. In the strong interaction, in like that alpha decay I just showed you, the number of neutrons and protons conserved. Okay? Here, I change a proton into a neutron or a neutron into a proton. This is fundamentally changing the particle. It's an extremely unusual force. Okay? And it's weak. It's not strong. It has a coupling that's very much smaller than the electromagnetic one. I get about 5 orders of magnitude, and therefore it's about 7 orders of magnitude less than the strong interaction. So it doesn't happen very often, but because it's energetically favorable for the nuclei to change from one type to another, if it's odd, it wants to become even, this is the way it can do it. It can change its numbers of protons and neutrons and move down that curve. So it gets to the ground state. So, yeah, so this is the motivation of what's happening. You have, what did I want to discuss on the board? Oh yeah, Fermi theory. Now I'll just draw one picture because I'm running behind time. I thought I wasn't going to have enough material, but anyway, okay. I talk too much. This is described, if I have a neutron, proton, electron, neutrino, by a simple compact vertex describing a neutron breaking into these 3 other things, okay? And this is parameterized by a constant called G Fermi. And if I look at Fermi's golden rule, essentially the matrix element squared, the quantum mechanical bit that we really are interested in, is just a number. It's just a scalar number, very small one. And this describes the theory. And this is Fermi theory of beta decay. And it was a real triumph for Fermi that he could describe how beta decay works in this way. Of course, he had to do something a little strange, introduce this neutrino, which has the added bonus as you can't see it. So it's basically saying, yeah, I can figure all this out if I tell you there's something that doesn't, you can't see it, but it's making the whole thing work. Okay? But there was good experimental evidence for that. Because if beta decay was just this, the electrons would be monochromatic. Okay, they would only, the electrons would, this, if you saw the kinematics of this, you would have the nucleus and the electron going out back to one another. So these are the momenta. And momentum conservation in the center of mass frame, or the rest frame of the nucleus, means that they have to have a fixed energy. Okay? But what you see, if you look at the absolute value of the momentum of the electron, is a smooth distribution. So this is the rate as a function of energy. And it goes right up to this maximum value. Yeah. So the neutrino could explain this shape if you just had an invisible massless particle. This shape can be explained, and that's what he does in Fermi theory when you work out the density of states factor. So this was well understood, but he expected the neutrino would never be observed, and we did observe it. I'm not going to have time to talk about that, but it's a very intriguing particle, and it only interacts weakly. But there was something even stranger about beta decay, which was discovered somewhat later, is that it violates parity. Okay? Now, parity is just the transformation of your coordinates from positive to negative values. This is what's known as an improper transformation. And as such, what it's really doing is changing a right-handed coordinate system to a left-handed one. Okay? That's all it's doing. Okay? Coordinate systems, as you know, are our choice. They should not affect how physics behaves. It's something we impose on the system to help us describe it when we do our calculations. However, when you look at beta decay of a nucleus with some spin, they all have some spin because of how the angular momentum is conserved. This was first done with cobalt-60. The spin can be aligned using a magnetic field. You can look at the direction of the momentum of the electron that comes off. Now, these are two different types of vectors under parity transformation. A spin is like an angular momentum, which is the cross product of two regular polar vectors, so it doesn't change sign, whereas the momentum changes sign. So if I invert all the coordinates in momentum, minus px component goes to minus px, and so on and so forth. But the observation is this happens far more often than this. They're not the same, which means that I can define left-handed and right-handed via this process. This is the frame in which the spin and the momentum are more aligned. Is the one that's left-handed. It's actually the one that's left-handed, and this one's the one that's right-handed. So this is really surprising. Nature, as you know it, doesn't tell any difference between left and right. Electromagnetism, if you do parity transformation on Maxwell's equations, you get Maxwell's equations. Yeah? So electromagnetism's just fine. Also, the strong interaction is also parity invariant, but that's a bit harder to prove, but you look at the Lagrange unit, will be. Okay? Okay, so that's all I wanted to say about decays and this violation of symmetry. So this was first observed in nuclear decay, but really underpins a lot of what we do in particle physics. Okay, so I'm going to move to the two applications and then a bit on particle physics. So this diagram of the binding energy, which I keep coming back to, what it means is if I fuse together nuclei with a mass less than that of iron, I gain some energy. All right? So this is getting more and more tightly bound. So if I can push things up towards that, I'll liberate some energy. So this is fusion. And then if I separate stuff that's out at large values, I tend to gain some energy because of how the pairing and the Coulomb effects are being reduced when I come back towards iron. So fission's your bomb, Aditya, okay? But now actually it's not your bomb, it's fusion. It starts the bomb and then it's fusion after that. And it's all very messy. And it's also energy. But fusion's the sun. And I'm not going to have time to talk about this more thoroughly, but all of life is due to this particular sequence of events. This is how the sun burns, or at least 85% of the sun burns. You take 6 hydrogen nuclei. You first of all fuse 2 of them together, and via a weak interaction involving a neutrino, which is the key bit I wanted to emphasize, you get a deuteron, which then fuses with another hydrogen to get helium-3. Then 2 helium-3s come together and form helium-4, which is tightly bound, and you've gained some energy in this process, okay? And there are 2 protons left over, but essentially you take 6 protons in, 2 protons out, 1 helium nucleus, and you get this little bit of energy. A little bit of that goes away in the neutrinos, but the rest takes 100,000 years or so and propagates out from the center of the sun, and the sun shines. All right? If we could do this in a lab, it would be fantastic. It would be a clean source of energy. That's the whole drive to do thermonuclear fusion in a controlled way. Unfortunately, this is really hard. So the state-of-the-art project is ITER, the International Thermonuclear Experimental Reactor, which is in the south of France, where it's a building site in the south of France. It was conceived in 1978. I was 4. It was approved in 1988. You do the math, how old I was then. And first plasma, which is the stuff needed to actually have a fusion reaction, will be in 2034. I'll be 60. So it's incredibly slow progress. But there is no physics in this. This is purely an engineering problem, a very, very difficult engineering problem of constraining the plasma and being able to do the heat transfer that comes out of this. And maybe as an example of why this is so difficult, and even the management say it's so, I found this today. So the importance of documenting failure was published in Nature Physics last year. This guy, Pietro Barabashi, is the head of ITER. Okay? So why he's thinking about failure should be apparent to you, given he's in this nearly 50-year-old project, which is not going as fast as it can do, because it's extremely difficult. Okay? I agree with him. We should document failure. You actually learn more by failing than you do by succeeding often. But I found this slightly amusing, that this is really where fusion is today. Yes, Rishi?
So could you go to the previous thing? So can we say that deuterium is more stable than hydrogen?
No, hydrogen is stable.
Then why do we have release of a neutrino then? Is it release of some error of some sort?
Okay, so protons do not decay. They are stable. But if I put together a proton and a neutron, that is more tightly bound. Okay, so deuterium has some binding energy associated with it, whereas a single object, the concept of binding energy means nothing, right? It's an isolated object. But to say it's more or less stable doesn't really mean anything. They're both stable. If you leave them alone, they'll both sit there forever. Okay? If you disturb deuteron a little bit, it decays. If you give it enough energy, the neutron and the proton will be driven far enough apart so that they're happier off alone. Okay? So far, we've never seen a proton decay. Okay. I'm sort of running out of time a bit. So now, a little bit of atomic physics now. I've already talked a bit about this. So we solve for that potential down there, and then we put in a load of corrections. One is relativistic. The electron's got isn't truly classical. It's moving a bit too fast. That's easy. Spin-orbit interaction is this business of the intrinsic magnetic moment of the electron in the field of the proton moving around it. There's this Darwin term, which is due to the fact you can't truly localize an electron. A little bit to do with the uncertainty principle. It's a bit of a fudge, but it's there. Then there's this thing called the hyperfine interaction, which is due to the fact that the proton has a spin and the electron has a spin. Now, this is intrinsic spin. This is of the electron, and it depends on its charge, its mass, and then there's this G factor, which the Dirac equation, the relativistic quantum mechanical equation, says should be 2 exactly. It's not quite 2. And then a similar thing for the nucleon, where we have the mass of the proton, the nuclear spin, and then we have this G factor. It's not 2. And the fact it's not 2 is telling you that the nucleons are not fundamental fermion particles. Again, that's a talk for another day. But what this means is if I look at the spectra from the hydrogen atom, this is the ground state. And all the perturbations move this around a little bit, but don't break the degeneracy. But this hyperfine interaction does break the degeneracy. In one of these, the spins of the proton and the neutron are aligned with one another. That's a spin 1 triplet state, and then you'll have a spin 0, F equals 0. So they call the combined spin of the neutron, the electron, and the proton F. And so it can be in a spin 1 state triplet or the 0, and it splits these two states. And essentially, this is the most common transition in the universe. It's quite low energy, but as the universe is largely hydrogen, the bits we can see is hydrogen, that this transition is happening all the time as the spin flips of the electron in the ground state. And this is extremely useful for doing radio astronomy. So this is the so-called 21 centimeter line, which has a wavelength of 21 centimeters today, but as you know, with all astrophysical cosmological observations, if you go back in time, it gets redshifted. So depending on the wavelength of this transition, you can actually tell how long ago it was. First thing that's useful about it. Second, it's a radio wave, so it's relatively easy to detect, and you can set up these arrays. So this is the square kilometer array, which is being built in South Africa. And you can essentially look back to times just after the cosmic microwave background was produced. Okay, so this is the first time that hydrogen was made. Before that, there were no atoms. Okay, so the universe was just a plasma, so no light could propagate through it. Then, once everything combined, there was a period called the Dark Ages, because there were no stars at that point. There was just hydrogen, and hydrogen was distributed around. But and there would have been photons around, okay? Some of which are in this particular wavelength because they were mediating this transition. Then they all clumped together and stars started to form, and they were so bright and so energetic, they ionized the hydrogen again, okay? So this is the period of reionization. So again, it was like a plasma-like period, and it's very hard to see through this bit. But with this 21 centimeter, you can actually look back into this region, and it's hoped that you'll be able to understand more about the evolution of the early universe by studying that period. They will also do tests of cosmology, dark energy. They will look for exotic phenomenon. It's a very interesting project. Okay, but again, it's just driven by a nuclear effect. It's a nuclear magnetic moment splitting the degeneracy of the ground state that does this, okay? And we also learn a lot about nuclear spins from hyperfine structure. All right, so I'm going to talk about particle physics. This is another talk in itself. This is the standard model of particle physics. You've probably seen some variant of this over time. We have these quarks, which feel the strong nuclear force, what we call quantum chromodynamics. And that's mediated by a massless particle called the gluon. Then we have the charged leptons, which also, now being charged, feel the electromagnetic force. And the quarks are charged as well, so they feel the electromagnetic force. Then we have our neutrinos down here. They only feel the weak interaction, so they only couple to the W particle and the Z particle. The Higgs is required to give these two mass. As a bonus, it gives mass to everything else. Okay? That's it. Most of the mass in the universe has got nothing to do with the Higgs. As I told you at the beginning, the proton is 3 quarks. So here, up, down, so it's 2.4 mega electron volts, 4.8 mega electron volts. The proton is 938 mega electron volts. The thing that is giving it mass is E equal mc squared, the energy that's holding those together, which is all in those gluons. So it's the energy of the gluons which is really giving mass to particles in the universe. Okay, so that's a talk for another day. This is great. We've built this up over 50 years. It works incredibly well. But we still don't understand certain things. Don't understand dark matter. None of this bit here can be anything that can be dark matter. It certainly doesn't explain dark energy. There's nothing obvious that's the inflaton. Possibly the Higgs field could be driving inflation in the early universe. We don't understand why we live in a matter-dominated universe instead of an antimatter-dominated universe, or an equal measure of the two. Then there'd be no structure. Neutrino mass is not explained by the standard model, and also why we have all these different particles with different masses and parameters we have to put in by hand leads to fine-tuning issues which clearly aren't very natural. But a lot of this was intuited from things we learned in nuclear physics. So firstly was about the Quark model, the so-called eightfold way. Early days of nuclear physics, Heisenberg came up with the idea of isospin, which he said neutron and the proton are the same particle in two different states of so-called isospin. This is explaining the fact that strong interaction didn't seem to care whether something was a proton or a neutron. So it becomes a doublet of this isospin. So the spin up one is the proton, isospin up one is the proton, the isospin down one is the neutron. And if you've done anything with quantum mechanical spin, you know you then can combine them in different ways and build up the singlet states, the triplet states, so on and so forth. So he did this so he could use that language to describe different states. Now this was carried over by Gell-Mann to start understanding the quark composition of the particles that were seen. So what I mean by this is this axis along here, it's called I3 here, it's T3 in most of the nuclear physics books. This is the isospin. So the pions are an isotriplet. They're made up of two isospin half objects, an up type or down type quark and an anti-up, anti-down type quark. These are both in isodoublets. You make a combination of those isodoublets and you get a singlet state and a triplet state. And he then extended this idea to a third parameter, which is strangeness or weak hypercharge, not hypercharge, not weak hypercharge, hypercharge. And this could then explain these strange particles as well. And this whole pattern came out of these very basic ideas that were there initially just to describe the neutron and the proton. So our idea of quarks were then confirmed using what's called deep inelastic scattering, that we could see inside the proton and we could see the quarks and the gluons that are there. So that's one example. This is a very complicated one, but I think it's one of the most interesting ones, is the fine structure constant is not a constant. Okay? So the fine structure constant, you may have come across, 1 over 137. But if you measure it with different values, take your time. Of the momentum transfer of the photon involved. So if I use a photon which has got the energy of the Z boson, which is a 90 GeV, the coupling strength has gone up to 1 over 127. Now, for the strong interaction, it's the opposite. As I go up in energy, the coupling gets less. And this is something referred to as asymptotic freedom, that essentially your quarks and gluons feel less attracted to one another the more energetic they are. Okay? This, wrong slide. This slide is what I wanted next. How this works is to do with quantum fluctuations. So once you start believing in quantum field theories, you realize that everything is possible, and you've got to account for all those possibilities. And one of the things that you have to then do is something called renormalization. And that means that things aren't constants anymore. It depends about how you're viewing them. And the simplest way to view this is with these little bubbles up here. So you have a photon, it's got little bubbles in it of an electron and a positron. Now if that's around a charge is always sending out these photons to couple with other things. And these little bubbles have got a positive charge and a negative charge in them, and say there's a positive charge in the center. It's like a little dipole, okay? And that the negative charges are more likely to be nearer the positive charge. This is polarization. It's like a dielectric, and you know what happens to an electric field in a dielectric, right? It gets reduced, okay? So when you're further away from the charge, you see a smaller charge. That's all that's happening, because essentially the vacuum is like a dielectric, okay? It's a little more complicated than that, but it's 7:20 in the evening on a Wednesday, so I'm not going to do anything more detailed. But that idea allows you to understand this running or changing of the coupling constant. Here they've inverted the axes, that they're doing 1 over Q here, so it's falling for the electromagnetic and rising for the strong. So there's a big difference when you go to the strong interaction, and from these two diagrams, can you see what the difference is? What do photons couple to in general? What must an object that sees a photon have a certain property? Charge, yeah. So when you do all your principle of superposition in 102, you're relying on this idea that the photon does not see other photons, right? So you can build up distributions from different charges that are there, and they're just going to sum up and give you the overall field. Can't do that with the strong interaction, because the gluons see one another. The gluons themselves are charged, okay? So this is why I have little bubbles of gluons here. So now, it's not that simple polarization model that I have for how the vacuum behaves with these little loops in the gluons. Sometimes there's red, anti-red, and it all has to sum up somehow or another. And it turns out it works the other way. It means that it's anti-screened. So the further away you are, the stronger the force looks. Okay? It's the math works out when you do this. It's complicated, but it does work. And that means that you've got to work really hard to move things further apart from one another. And it leads to this confinement of the particles within the nucleus. So just to better understand that, well, I don't know if better is the word. Yeah, maybe I should not talk about that. I should stop. I can ask me about it. But this is this confinement idea where you have two quarks, and they've got a gluon field between them. And as you stretch them further apart, the scale getting longer, it actually becomes energetically favorable with the energy you've put in to pull them apart to make two new masses. And these things cancel each other out. They're now colorless, so this region doesn't have any strong force in it anymore. So I didn't really talk about color. I didn't have enough time, but this is important for how these particle level strong interaction works. But basically this leads to this confinement. So the hadron jet bit, ignore, this has come from particle physics. But essentially these ideas about the confinement again led to the ideas of how we develop QCD, and that goes into the standard model. Okay. I'm going to stop because I've talked too much. I'm also hoarse. I won't talk about chiral interactions. Do ask me. I could tell you lots about neutrinos, but I will conclude. So there's lots of applications. There's medical ones, NMR, PET scans, hadron therapy, all of these nice things. There's dating, not Tinder-based, but carbon-based. And then, whatever. I forget. They've got nice names here, these dating agencies, but I forget them now. Then energy we've talked about a little bit, and then there's defense. Some of you may have watched this on Netflix to realize it isn't really defense. And for me, the importance of nuclear physics was the way lots of people started to get ideas to understand the particle world. and now it's also informing cosmological things. Sorry, bit chaotic, but I didn't quite know what you wanted to know, how these normally go, because I don't attend them. But I'm happy for you to ask me anything about particle physics and nuclear physics, not about dating. We can stop there. And you want to have your snacks and stuff now, probably. Okay, thank you. Yeah.
So why was the binding energy called semi-empirical?
So something that's purely empirical, you're just fitting some parameters to describe a shape, okay? But you've got no physical intuition about why it would have that functional form. Semi-empirical mass formula is you have these various terms which have some physical basis, volume, surface, Coulomb, whatever, but then you fit the parameters in front of them. Okay, so the parameters themselves are not calculated ab initio in some way, okay? It's fit to the data, so it's a two-way process. You have a model that's based on reasonable theory, but the parameters you can't predict, okay? Whereas full theory, you can do this. Yes?
At the start of the session, we talked about we can.
Oh, no. Yeah, carry on, Aditya. I'm listening.
We can model the nucleus as a particle in a 3D box. But
Well, that's a model, yeah. It's not quite like that, but it's close.
like, why are you not modeling it as a 3D?
So when I showed those levels for the infinite well, that was a radial sphere. So that was the spherical version. But your conclusions are not so different, okay? It's just the box is easier to do because you don't have to worry about all the angular momentum parts, and it's just an extension of what you do in one dimension. So I don't know how much quantum mechanics you've done, or you haven't done very much yet. You'll realize that the box is the simplest quantum mechanical thing to deal with. But the sphere is closer to the truth than a semi-infinite well is, and a semi-infinite well with a fuzzy boundary is perfect. And that fuzzy boundary is to do with the quantum fluctuations, that the nucleus isn't a sort of fixed potential because there's some motion, so some bits near the edge will not always be at constant values, but it can be averaged out to be that smooth shape. Okay? Yeah, there was another question? No.
How did you get to that odd and even?
So I'll go back to that slide. So here, when I have a pair of protons or a pair of neutrons, they will end up filling a certain bit of one of these states, right? Where you'll have both the spin up and spin down together, and they'll be in some ML state. They'll all be closed, right? So it's like a proper filled shell, okay? When I have odd, I have one unpaired neutron and one unpaired proton, and they don't pair up in exactly the same way that's going to be stable. Hence, that tends to be less well bound, okay? That's the reason. So you end up with so you have a so-called pairing term in the semi-empirical mass formula, which is hard to draw on that curve because it's the same for it's different for every A. So it's like that A is a band, basically, but the more even nucleons are more tightly bound. And so this is for variable Z, fixed A, you draw these two curves, and then you can find out you can essentially work out the energies of the beta decays, and it's quite accurate. Yeah, it's a part of the empirical bit. But the semi bit is what I told you about the pairing. Okay, the pairing is preferred because the force is spin dependent. But it has to be truly identical particles at that point. Yeah. Yeah. So
You talked about gluons, neutrinos being massless. I actually don't get what's the notion of being massless. You don't have mass, but you have charge.
Yeah, we don't have a mass. Well, they have a weak charge, so they are charged, yes.
There's nothing there, but it has a charge.
But you're being very prejudiced. Sorry, I should explain that before he takes offence. You're thinking electromagnetically. Weak interaction, it's fully there. It's a fully paid up member of the weak interaction. It's got a weak charge or weak isospin charge. It's actually the same charge as the electromagnetic one. I didn't talk about this, but in particle physics, the two forces are unified. The only difference with the weak interaction is you've got this really heavy W boson, which makes it appear weak. But it's actually stronger, the weak coupling, than the electromagnetic one in the standard model. Okay? And then there's a lot of stuff that's done to sorry?
You want the massive by LED?
I'm not understanding.
Like, I had the idea that gluons and neutrinos are massive.
Yes. So a photon is massless, right? Photon is a massless particle. It's actually when you do field theory, massless is much easier than massive. Because all the gymnastics we do to motivate the Higgs boson in the standard model is just to give the W and the Z mass. The standard model would be much more elegant if all the force carriers were not massive. Then I just have simple Dirac terms. I wouldn't even need any of this. It's not quite. There's some advantages to the Higgs and Yukawa couplings, and there's vacuum stability and things, but it's actually more natural to be massless than massive. Masses are numbers we put in by hand. We don't understand. Okay.
Why do you have proton and neutron relying only on lower atomic?
Sorry?
The next slide you have.
Yeah. So, because when you get to more massive ones, you can form the helium nucleus. When you're in the low mass ones, you have less probability of fully forming the helium nucleus and having alpha decay. So you have to survive with just spitting out a single one. And the deuteron's too weakly bound to be something that's useful in this way. Okay? So it's really when you get that tightly bound helium nucleus that you get a big advantage, and that becomes, then you're just pulling out individual protons or neutrons. Okay? I mean, which is easy to see why that would be energetically favorable, right? Yeah.
So when we talk about the particle, antiparticle from the photon, right, those processes, don't they get like diminishingly small as you take higher and higher orders? Like getting like fair particle production, 3 different fair particle productions, don't they become diminishingly small, 3 or 4?
So, no, there's a certain order to a process. Then there are corrections at higher order to that. So those corrections can get diminishingly small. But the leading order process is what it is, and I will calculate the probability for that, and that will happen. Then I have to correct that for the higher order versions, okay? So it doesn't suppress the thing as a whole. It just means that the corrections get smaller and you get a converging series, essentially. Doesn't work in the strong interaction because my coupling tends to 1 or greater when it's very low energy, and then I have a problem. Okay? Yeah.
So thanks all for coming. We would like to conclude this session by presenting a small gift to the professor.
Okay, thank you very much. Thank you, Asim.